everyone, and welcome back to this series on R programming. Today we're going to be discussing some of the very important techniques that you definitely should know when you're working with a little bit of linear algebra. As you probably already know, linear algebra has so many applications in practically every field, so knowing how to use linear algebra in whatever programming language you want to be proficient in is definitely a must. So let's get right into it. So the first thing, if you want to, play with linear algebra in a programming language, is how to define vectors and matrices. And keep in mind, a vector is just a one-dimensional version of a matrix. So if you know how to make matrices, you know how to make vectors as well. So how are we going to create matrices? So I'm going to define a matrix A, and A is going to be equal to a 3 by 3 matrix. There's a couple varieties of ways you can define matrices in R, but one of the ones I find a little bit more useful is where you define it row by row or column by column, provided that you know the entries in that matrix you want to define. So let's go about this in the row fashion. So if you want to bind rows together, you use a function called rbind or row bind. There's also another function called cbind, which will bind columns together. So what we want to do is we want to bind 3 rows together. So the first row, which is going to be a concatenation of 3 elements, in particular -2, -4, and +2, that's going to be my very first row. And we want to rbind that row with the next row. And the next row is going to be -2, 1, and 2. And then we're going to rbind those 2 rows with a third row. And that third row needs to be 4, 2, and 5. Something very important, if you're going to be R binding or C binding things, the lengths of each of those vectors, whether they be row vectors or column vectors, must be the same exact length, else R is not going to be very pleased with you. So once we have that A defined, then we're going to just run that little line of code, and then we're going to have our matrix A defined in our environment. So if we go down here to our console and display the value of A, you can check to make sure that it is indeed displaying your matrix as you intend it to be. So we have -2, -4, 2, which is our first row, -2, 1, 2 as our second row, and then 4, 2, 5 as we desired for our third row. Right. Now, another way you can define a matrix is a little bit more general. For example, let's assume that we want to just create a matrix that has a specific type of dimension, and let's just fill that matrix with a bunch of numbers. In particular, let's assume that we want to create a matrix of 20 random numbers associated to a standard normal distribution, for example. So to create random numbers associated to a random normal distribution, we're just going to use the rnorm function, and we want 20 of them. Now the matrix function needs you to specify how you want those 20 elements rearranged. So you're going to have a number of rows and a number of columns, and the product of those two numbers has to be 20, right? So we can, for example, do 1 by 20, 10 by 2, 4 by 5, or other variations if you want. So let's assume that the number of rows that we want to work with is going to be 5, and let's assume the number of columns we want is going to be 4. So it's going to rearrange these numbers from 1 to 20 in an array or a matrix of dimensions 5 by 4 dimensions. So once we give that a run and display that particular vector, that's going to give us your 5 rows by 4 columns matrix, which I've defined as B. Right? So that's how you can define a matrix in that fashion if you just want to fill that matrix with a bunch of random numbers, or you might have vectors already defined ahead of time, and you can just C or R bind them as necessary as long as this n row and n column match as desired. Okay, so now let's see how we can maybe combine matrices together. So let's assume that we have this matrix B, which is a 5 row by 4 column, and let's assume that we want to put another column in front of, for example, this first column that we have here, because we have column 1, but let's assume that we want to put a column to the left of it. In particular, let's assume that we want to put a bunch of 1s in front of that. So when we put another column, we're going to have 5 columns now and still 5 rows. So let's assume we want to introduce a vector that has, for example, 5 1s associated in a column. Okay, so the first thing I want to do is create the structure that I want to append to that matrix. And let's call it v1s for a vector of ones. And how you can create a vector of ones instead of doing, for example, 1, 1, 1, 1, 1, we have a shorter way in case you don't already know it. What you can do is you can use the repeat command, and we're going to repeat the number 1 5 times. So in case you're not familiar with this function, if you do v1s and display that, that's going to give you 1, 1, 1, 1, 1, which is a vector of ones. Now, in its current state, it's not necessarily defined as a column or row vector, but whether you c-bind this or row bind this to an object, it will transpose it as necessary. So I want to treat this vector as a column vector, so I'm going to c-bind this to the matrix B. Right? Now keep in mind, in order to c-bind this to B, the number of rows of this vector must be equal to the number of rows of this vector. But we already know that this is going to have 5 rows, this already has 5 rows, therefore we can column bind this vector as a column to that matrix. So I'm going to create a new matrix, I'm going to call it B new, and I'm going to c-bind the vector to the front, right? So I'm going to do v1s, and then I'm going to bind it to B. If you want the v1s on the right, you just do B comma v1s, and that will put it on the right. So once we do this, let's just make sure it gives us what we want. So there's our original 5 row by 4 column matrix on the right, and then we have our column of 1s situated under that name v1s. Okay, so there's our new 5 rows by now 5 column matrix. So that's actually pretty nice. Now, once we have a bunch of matrices, obviously there's several operations that you can do with these matrices. For example, you can add them, subtract them, multiply and divide them. As long as the matrices or vectors have the same exact dimension, minus and plus will work in the same exact way. And in case you don't already know, you cannot, at least inherently, divide matrices. So matrix multiplication is the only one that needs to be mentioned. Now, there's going to be 2 different types of multiplication. There's going to be this symbol here, which is your typical order of operations multiplication. And then there's another operation, which is going to be represented by percent star percent. So percent star percent will be your typical matrix multiplication, and star will be element-wise multiplication. So element-wise multiplication only works if your vectors or matrices have the same size, and you, for example, multiply element 1, 1 with 1, 1, 1, 1 with 1, 2 with 1, 2, 1, 3 with 1, 3, and so on. But this is your typical inner product approach where you take a row and you dot product it with the first column, or the first row with the second column, first row with the third column, and that gives you the elements of the new product matrix. So this highlighted one is the one that we're going to be working with. All right, so let's see how we can create a new vector. Let's include, for example, multiplication. Let's do a little bit of transposes where the rows become the columns, and also discuss how to do inverses of matrices as well. So if you want to do, for example, transpositions of matrices, all you have to do is just T of B. So that's going to give you a transposition. If you want to invert a matrix, now keep in mind the number of rows and columns must be equal to invert it. All you have to do is just do solve of B, and that's going to take the inverse of this, right? Now, in case it is not in the correct dimension, it will throw an error at you, because notice that 5 by 4 must be square, and obviously 4 and 5 are not equal to each other. But keep in mind, we did append a vector in the front of this to make it a square matrix, and we called it B new. Therefore, since that is a square matrix, then it should have an inverse as long as it is invertible. Now, obviously, if you know any theory about invertibility of matrices, another calculation that you definitely should know is determinants. So as long as the determinant is not equal to 0, then we know that the matrix is invertible. So in order to calculate the determinant, just do determinant of B new. That's going to give you this number, and as long as the determinant is not 0, and technically far from 0, then it should be invertible and stable. Okay, so those are just some of the things that you definitely should know when it comes to these. So let's actually do a little calculation with our B new matrix. Okay, but let's actually create another vector. For example, let's create y to be equal to a vector in column form. Let's do 4, 9, 8, 9, 1, 2, and 12. Right? So here I've created a vector that has 7 entries. Okay? So that's going to be my vector y. And actually what I want to do, I don't want to use 7 rows here. Let's see if we can match actually are the dimensions of B or B new. It doesn't really matter. But before I get into a redefinition of Y, let's actually calculate something that's actually really common in regression. And that's XTX inverse XTY. So let's do XTX inverse. So how do you do XT? So that's going to be the transpose of some matrix. Let's actually work with the matrix B because we know that that's not a square matrix. So XT, X, or BTB, right? So that's going to give us the inverse of some matrix. And in case you don't already know, if you do B transpose times B or B times B transpose, that's always going to result in a square matrix, hopefully invertible, and hence it has an inverse. So that's going to be BTB inverse times BT, and then we're going to multiply this object by some vector. Notice that we have 5 columns here, so we can multiply it by a vector that has 5 rows. So let's go back up here and delete a couple of columns. So this is going to have 5 rows because it's a column vector, as we have here. And then let's multiply this product by y. Okay, that's going to give us a vector that has 4 rows and 1 column. And if you know anything about, for example, multiple linear regression, then you'll know that this is, for example, the intercept term, most likely assuming the first column of this was 1s, which it's not. But this process, this type of calculation for matrices is extremely, extremely common. Now that we've gone over some of the basics associated to matrix multiplication, matrix transposition, inverses of matrices, and creating matrices, now let's talk about very important things, in particular eigenvalues, eigenvectors, singular values, and singular vectors, and a couple little side things associated with that, right? So if you don't know what an eigenvalue is, just know for now they're very, very important in applications, right? And there's plenty of resources out there, and I have a couple series out there as well on linear algebra and eigenvalues if you're interested in checking that out. So, in case you don't know what an eigenvalue is, the important thing that you definitely should know is the following. You can only, at least traditionally, calculate eigenvalues for square matrices. And if your square matrix has n rows and n columns, it's going to have exactly n eigenvalues. And in order to find these eigenvalues, there's a very nice function that is called eigen. Right? So eigen is actually going to find 2 things for you, right? And let's go ahead and redefine our matrix A there, right? So eigen is going to find 2 things again. It's going to find eigenvalues and normalized eigenvectors, okay? So our eigenvalues, if you want to access them, we're just going to do $values, and that's going to give this 3 numbers because we have a 3 by 3 matrix, so 6 minus 5 and 3, so this is the eigenvalues of this matrix. And the eigenvectors, $vectors, that's going to give us the eigenvectors, and they're going to be in the same exact order as your eigenvalues. So if you have 3 eigenvalues, you're going to have 3 scalar multipled eigenvectors. Now, in case you don't know what eigenvectors are, there's actually infinitely many of them associated to a particular eigenvalue, but they're just scaled multiples of each other, right? So these are all unit vectors of length 1, for example. So 6 has eigenvector 0.05, 0.35, 0.93. 3 has eigenvectors 0.53, negative 0.80, and negative 0.27, respectively, right? So those are your eigenvalues and eigenvectors. Now, most of the time we would like to store these eigenvectors in a matrix. I'm just going to call it M. And most of the time we would like to store these eigenvalues as a diagonal matrix of size, the same size as our original matrix, in this case a 3 by 3. So to create a diagonal matrix with our eigenvalues on the principal diagonal, all we're just going to do is define a new matrix D and use the function diag of that vector, and that's going to create a diagonal matrix with those eigenvalues on the diagonal. So if you look at D, now we have 6 minus 5 and 3 are eigenvalues on our principal diagonal. Right? Now, one of the very beautiful things of eigenvalues and eigenvectors, if these eigenvectors are linearly independent, i.e. the determinant of this matrix M is non-zero, which in this case it's not, is that matrix is diagonalizable and has something called an eigenvalue decomposition, which has a lot of applications, which I'm not going to get into here. But the eigenvalue decomposition would be equal to M times D times the inverse of M. Right? So keep in mind, what was our matrix A? Our matrix A was this matrix here, our nice little matrix. And if we evaluate MDM inverse, you get the same exact thing, right? So we call MDM inverse the eigenvalue decomposition of A. Now, the little downside about eigenvalue decompositions is that only a subset of square matrices has them. And that's, kind of sad. So not even every square matrix has eigenvalue decompositions, just a subset of them, right? And keep in mind, if you have a rectangular matrix, traditionally they don't have eigenvalue decompositions. So the natural question is there a decomposition for any matrix? And the answer is, of course, yes. There's a few of them, but one of the more famous ones of them is called singular value decompositions. Right? So in order to find the eigenvalue decomposition of a matrix, there's a very nice function, and it's just called SVD. So S is going to be defined to be equal to the SVD of A. So again, S is going to be a structure, and it's going to have three things now. It's going to have things called singular values, left singular vectors, and right singular vectors, right? So before we had eigenvalues and eigenvectors, now we have singular values and left and right singular vectors, right? And they're all stored in this object that I've defined as S. So the left singular vectors I'm going to store in a matrix U, and this is going to be equal to S, and it's going to actually return it as U. And then we're going to have V, which is going to be equal to S dollar sign of little v. And then we're going to create another matrix, a diagonal matrix, and I'm going to call it sig. And this is going to be equal to the diagonalization of S dollar sign D, the singular values of that matrix. Okay? So if we look at U, those are the left singular vectors. If we look at V, those are the right singular vectors. And if we look at D, the diagonal entries, those are our singular values. Now, if we compare that to our, those are my singular values, my eigenvalues. Let's look at D, or sig as I called it. Those are our singular values, okay? So, how are we going to get a decomposition out of this for our singular value decomposition? Let's erase D so that doesn't confuse anyone. So the singular value decomposition is actually going to be equal to U D V transpose. So instead of MDM inverse is UDV transpose. And if we look or remind ourselves of what A looked like, and if we multiply this out, notice that, it doesn't give us the same exact thing. Well, is that normal? Actually, it's not, because the decomposition should give us the original matrix. But do you see the little issue I had? Because is D the matrix that contains our singular values? No, that should be sig, right? That's usually why you always give them meaningful names, right? But this is usually abbreviated as sigma, right? Which I'm not going to go through the hassle of typing in R, right? But if I multiply these out and compare to A, notice that now I do have that matrix, right? And this U sigma V transpose is indeed what we call the eigenvalue decomposition. Right? So that's actually very, very useful. Lots of applications there as well. Now, another little side number that you probably should know is what is called the condition number for a matrix. And this has a lot of applications in stability theory for model building. So the condition number, which I'm going to call knum, is going to be equal to the maximum singular value, which is an S dollar sign D, divided by the minimum singular value. So max divided by min singular, right? So if we look at this number, notice that we have 2.54. Generally speaking, low condition number that is close to 1 is very, very safe. Large condition number, bad, right? Now, how large is large? That's another theoretical conversation, but generally speaking, the closer to 1, the better. Right? Now, there's several other things associated to linear algebra out there that you probably should know, and it's possible that base R doesn't have it, right? So you can always install some packages in order to include more topics. For example, if we look at this matrix A, obviously if we take the inverse of this matrix, we get an invertible matrix. So that means if you know anything about reduced row echelon form of this matrix, that means the rank is a full rank matrix, i.e. the rank of 3, which means that the reduced row echelon form of a 3 by 3 should be the 3 by 3 identity matrix. So if we just blindly see, does R have a RREF function built in? And it's like, oh, I can't find that function RREF, and that's, kind of sad. But a nice little library that has a lot of linear algebra things is called, and I'll just introduce it here right quick, is called PRACMA. Right? So that's a very useful package that contains a lot of linear algebra tools. So once you have that package all installed, then of course we need to include the library, which I'm going to call again PRACMA. That gives us access to all of our things, and sometimes it will give you a warning message, especially if it was built for a previous version of our studio. And then one of the functions that it does have is the reduced echelon form of that matrix A. So obviously when we reference that matrix that is invertible, we obviously see that it does give us an identity matrix. This library obviously has so many more things associated to it aside from reduced echelon form, but I'll let you explore that on your own. So those are some of the important things they definitely should know when it comes to using linear algebra in R. Hope you enjoyed this little tutorial, and I'll see you in the next one. Take care.